Hello, my name is Nick Clausen with Dental Laser Coaching, where our goal is to make the complex simple and transform your practice with dental lasers. So the first presentation today is going to be on laser physics. Laser physics is a complex topic, but it's crucial that you understand the basics of laser physics in order to operate your laser to its optimal potential. Because if you don't understand the energy that's coming out, how it's coming out, and some of the things that it interacts with or has an infinity for and how it works, you will never be able to optimally set up your laser and understand the proper techniques to make it work. So though this may be a little bit complex, it is crucial for you to understand. And my goal today is for you to understand the basics of laser physics so you can better utilize your laser. After this presentation, if you'd like a little refresher, I do have more links on the website that has how lasers work and specifically. It'll give you a little snapshot under the hood of lasers, as well as a little bit longer presentation on an overview of quantum physics that'll dive into this in much greater detail. But again, today I'm going to give you an overview so that you can understand the basics so that you know how to operate your laser efficiently and effectively. There are 4 classifications of lasers. The first, class 1s, are self-contained. You see this every day with your printer. There's a laser in there, but it's contained within the box, if you will, and the laser energy does not get out. The class 2 lasers are, again, low powered, but now we have exposure to that. An example of that would be a UPC scanner at the supermarket, a laser pointer, etc. The third type, or where we have exposure to it and we need eye protection. In our community in dentistry, this is very common with curing lights, cold lasers. Cold lasers are lasers that do not cut, but have other properties, which I'll get into later. And finally, class 4 lasers are the lasers that can cut and that we're used to using for various dental and medical ablative type procedures, and we definitely need to have laser safety glasses to protect our eyes. So as we all know, lasers is just an acronym for light amplification by stimulated emission of radiation. Well, what does that really mean? And this started off with Bohr and Einstein finished it, but basically what we're doing is we're taking an atom and we're applying some sort of energy to that molecule, and then that electron that is going around the atom gets excited and expands a state, what it's called, and when it does that, it releases a photon and goes back to its natural state. When it releases this photon, the photon is coming out, and that photon is released in a wave. And that laser wave that is released is consistent every time and does not vary if the same medium is used. And what I'm talking about here is there are different ways that we can do this. We can excite that atom with a flash lamp, some sort of electrical current, or a diode laser. The medium or the atom can be a dope crystal, a gas, a dye, or I mentioned a diode, and then we resonate that inside a cavity with mirrors and with various coated surfaces, again, which you can see in detail on a different video on how lasers work. But as I mentioned, this photon wave comes out in a packet of energy, and it is consistent. And this distance from peak to peak, as that photon is released and goes through space and time, is always the same. So the distance from peak to peak of that particular atom that it released the photon, we measure that distance in nanometers. So in dentistry, a lot of times you may have heard the term, I have an 810 diode, I have a 980 diode, I have a 906 diode. You're like, what does that mean? All that's saying is the manufacturer for that particular laser is saying that the energy that's coming out is in this particular wavelength from peak to peak. Nd:EGs are 1064, CO2s are 10,600 or 9,300. So those are some of those numbers that we're referring to, and we measure that in nanometers. So if we take a step back and look at that, what we have to the left of visible is what's called ionizing radiation. Or the photons that are coming out in very tight packets and waves, and we use this in x-rays, and they are harmful or ionizing to living tissue. That's why we have to wear a protective vest. So you can see here, everything to the left of visible is considered ionizing radiation. Now our eye can make out these particular wavelengths from 400 to around 700, and we decipher a specific wavelength to a color, and this is in the visible spectrum. Then to the right we have our infrared. Now this type of wavelength coming out is thermal, but it is non-ionizing. It will not break down cell structure, but it does have thermal properties. So that gives you an idea of what's coming out of the laser. If we zoom in closer to the visible, this is where more of our dental lasers are used. Excimer lasers are used in some eye surgeries, but in dentistry, most everything that we use is in this area right here to cut or ablate tissue. So you can see there's all these different wavelengths, and different wavelengths resort to different colors, or you visually can see these colors. So if we take a look back, these are the mediums and the type of lasers that are used in dentistry, and the wavelengths, these aren't exact, it's just a graphical representation, but this is what has been used in the past, potentially some things in the future, and that are being used today. So to get some key terms, just in general, laser properties, wavelength, which we just discussed, it could be discussed as a color, but most of the time it's invisible, and that is measured in a nanometer measurement from peak to peak. The pulse energy is measured in joules. And most of the time in dentistry we don't use that much power, so we refer to it as millijoules. And fluence is joule when we add an area. How much energy are we providing in a certain area? And the most common measurement is joules per centimeter squared. So a lot of times this is used for very, very important for tattoo removal, for fractional skin resurfacing, etc. Pulse duration is measured in milli, micro, nano, and even in the future picoseconds, which are very short bursts of power. Remember that lasers can be on all the time, but there is a thermal effect to lasers. They have heat, so we do not want to have heat necrosis when we're doing surgery. So that's why we pulse the lasers. And power is the energy that's delivered, and that's in usually watts, which is calculated in joules per second. And then hertz is basically that specific pulse duration, or how long is, this is pulse duration, how it's measured, but really its pulse is represented in hertz. Spot size is basically how big is the area that we're releasing energy, how big is the fiber or the tip, and most of the time it's in a round fashion. And then we want to cool, and we can do that by pulsating the laser with a hertz rate, or we can, which is a time function, or we can force cool air over the area to help cool. So to dive into dental laser power and energy terminology that's used by most manufacturers, again, these are the most common energies here, and we use millijoules for dentistry for the most part. And for example, in a dental laser is measured at, let's say, 200 millijoules, for example, for a erbium laser. And that is just the time that the laser is on. Hertz is the pulses per second, and this could be 1 pulse per second, or it could be 1,000 pulses in 1 second, or the laser CW refers to as it's continuously on. Watt is the unit of power. For example, 1 watt is measured in 1 joule per second. So if we wanted to calculate, for my example here where we had 200 millijoules per pulse, at 20 pulses per second, that would be 4 watts of power, because we take the joules, the millijoules that we have, time the hertz, and we get 4 watts of power. And the spot size. And again, this is a lot of times determined in dental lasers with the fiber selection or the tip size selection. And these are the crucial components. So hertz, just to recap again, is the pulses per second. So as you can see here in this graphical representation, if this is 1 second from the start to the end, we could have it pulsating 3 times per second, or in this case actually misrepresented it as 4, but it could be 3 seconds over 3 times in 1 second, all the way up to 50. So what is interesting here is that hertz can hurt because of what's called thermal relaxation time. We want to have as much time between pulsations as possible, so that tissue or cell can heal from that burst of energy. But sometimes if we're too slow, the tissue can, for example, if we're doing a gingival contouring, if we have very low hertz, the tissue cut will be very taggy and rough. So what we do is we teach you how to optimize the various settings to get your clinical objective without hurting the patient. So the other thing that's key here is watts. And watts, think of that as kind of the power behind the punch, how the energy is being released and how much power in that packet of energy. So what do we have here? Laser energy in dentistry is delivered 3 ways today. The first and most prevalent is by an optical fiber. You can see here, this can be done, an optical fiber, with our erbium lasers that we have out there, with a optical fiber that has a handpiece in the end, or we can use these in our diodes that we have today in a spool next to the laser, or in these small pen type lasers with a disposable tip. But that's one way. The other way is a hollow waveguide. Think of this as like a garden hose. Instead of a solid fiber, optical fiber, we have a hollow waveguide that the inner lining is coated. And this is a more inexpensive way to do it, but there are some limitations to this because it does affect the output on how much this fiber is bent. And then the third way to deliver energy, and this is done a lot of times with higher power lasers that have high peak powers, because we deliver the energy through a series of mirrors that are in the articulated arm there. So back to optical fibers, again, I mentioned the most common are erbiums. You can see here, this is would plug into the laser right here. The energy would then come out this end, and the diodes here have these different diameters, but they have a protective cladding. And if you remember from the old days when we used diodes, we had to have this, it was called a stripper. We would remove the protective outer jacket and sheath, and sometimes they were brittle or they would break. Most diode lasers or soft tissue lasers today have this protective jacket you can now remove with your fingernails, and these fibers are much, much better than they used to be. Erbiums, on the other hand, that have this optical fiber have, I mentioned, I was starting to discuss this earlier, where you plug it into the machine here, and then there's a handpiece that goes on with various tips. You can see here, this is just happens to be a photona tip, where they have various, you can see here, different diameters, lengths, and they even have a specialty tip here that called pips, where it used for endo, where it photonically induces, creates a shock wave and clears out endocanals. So there's various tips that you can put on the different hand pieces. But this is the most common type of fiber. There's this cladding in a core with this protective jacket. Now they can break or crack. If you get, and some of you may have done this, if you had a long diode fiber, you may have ran it over with the wheel of your chair, and it cracks it, and then it's ruined from that point on. Or if you had an erbium laser, maybe over time it cracked or broke, and those are very expensive. The older diodes, as I mentioned, can be brittle, but the new ones are quite flexible and they're easy to strip. And as I mentioned, this would be one long continuous fiber. We're talking about diodes now, and you cut a little bit off after every procedure, or you can screw on a tip that's you just throw away. It's disposable. With diodes on this fiber, we do what's called photoinitiation, and this is only done with soft tissue lasers. This is not done with the erbiums or the bone cutting or the CO2 lasers. It's just done with our soft tissue lasers. And what we do is we put this on a dark color or an active medium, and it does what we call initiate the tips. If we don't do this, it doesn't cut. And there are times, especially in hygiene or photostimulation, where we do not want it to cut. So it's very crucial that we do that if we want it to cut. And then when we're done, we cleave or cut a little bit off that fiber. Now just note, you score or put a little cut in the fiber, then you push and apply pressure. There is a science behind this, and you want to do a good cleave, and you want to make this as flush and clean as possible, because you want the energy to be coming out as consistently as possible. This will cause two problems if you don't have a good cleave or you have a bad fiber. One, this will act like a razor or a scalpel, and it'll cause a lot of bleeding, and it can break off and be left in the tissue. And if you do it this way, the energy is not coming out consistently. You want as straight as a cleave and as cut as possible. So if you do notice some problems, one way to check this is to take your laser, once you've cleaved and cut it, turn it on, aim it toward a white piece of paper, and you should have a nice circle there on the paper, and it should not have any flares coming out of the end. If you have flares, then the energy is not coming out consistently. So the other thing that we have then is a hollow waveguide. As I mentioned earlier, and I started to discuss, a hollow waveguide is less expensive than a fiber delivery, but it can be varied as the fiber is bent. So the energy output, even though you don't change anything coming out of the laser head, if this fiber is bent dramatically, it can affect the output at the target tissue. And it is limited to a certain length from a physics perspective. But again, a very reliable way to deliver energy. And then I mentioned the third type is an articulated arm, where the energy comes out of the laser, hits a 45-degree mirror, bounces, 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 and these are rotation points on the handpiece. And the mirror alignment is crucial. You can see here if the mirror alignment went off a little bit, you're not getting consistent energy out of the end. And they can be a little bit bulky, but man, they can handle high powers. And I've got a picture here of the new Solea energy laser here, and this is a new CO2 laser that's a new wavelength for dentistry at 9,300 that actually can cut hard tissue and soft tissue. But you can see here its articulated arm is counterbalanced with the weight here, but the energy is coming out of the tip, hits a mirror, comes out, hits a mirror, and hits another mirror. And I've also put this on here because this has a new feature in dentistry, and it actually has a series of mirrors. This is now the head and the handpiece of the laser, where it actually has computer-controlled motors that move mirrors inside the handpiece, and these mirrors manipulate the beam thousands of times per second. And this is what they call a galvos, and they're using computer-aided preparation to basically now be able to use a CO2 wavelength to cut hard tissue, which is quite exciting. So that's just an example of an articulated arm. So some of our modes of operation now that we know how the laser energy is created and how the energy is outputted by specific arms, tubes, or fibers, now, how do we release energy? We have three different options. We can have the laser coming out in a continuous wave. In other words, the laser is on and it stays on the whole time. Okay, it's not on or off. So this is 3 watts of power over 20 seconds of time. Or we can gate or pulse the laser. And here what we do is the laser is on, off, on, off. And usually, especially because in dental technology, most diodes and predecessor diodes and some of the more inexpensive diodes today are continuous wave, or they're on or off. And usually they're on half the time and off half the time. So in this example, our peak power is 3 watts, but since it's on half the time and off half the time, the average power is 1.5 watts, or the average power that's delivered to the tissue, as you can see there. And now what's important is when we start talking about pulsing the laser, it becomes harder and harder to make that energy consistent. In other words, when you're turning it on and off, you want it on for that amount of time and then off. And that's called flat top beam profile. That's very hard to do and expensive. Most lasers, you still use this Gaussian beam profile, which the laser energy is on, but it doesn't come to that flat top, and because it peaks and then it comes down, that can thermally be a little bit hot. So that may be some of the differences in cost. Some of these lasers may use this flat top profile when it's pulsated or hertz. Now the free running lasers, think of these as, instead of on or off, these are on for fractions of a second, and we have much higher power, but the average power is still low. So for example, here we could have a peak power at 1500 watts, but it's only on for 200 microseconds. So the average power is only 3 watts that's being delivered to the particular target tissue. When we can do this, it cuts much more efficiently and effectively, no matter what the technology, and there's less thermal damage when we can have it on for fractions of a second. And we can control how many pulses per second we want to do this, but this is just a graphical representation of some of these free running lasers. So continuous wave versus pulse lasers, well, continuous wave is going to be faster, obviously, but there's going to be more thermal energy. Whereas today we tend to be pulsating or Q-switching these lasers in milliseconds in the past to nanoseconds, and now it's called picoseconds, where it's on for an extremely short amount of time. So the shorter amount of time it's on, remember our term, our thermorelaxation term, the more time that the tissue has to heal. So as it represented here, it tends to stay in that target area as well. And when we have longer times that the laser's on, we tend to have energy creep, and that tends to cause harder to control, and the surrounding tissue may have some of those edema effects in regards to thermal necrosis. So that's just a summary of some of the laser technology, and these bodies are governed by different agencies, and these are the ones that you'll deal with in dentistry in regards to OSHA and the Center for Devices and Radiological Health, and the American National Standards Institute come up with all the standards for this medical and dental lasers. So that's the conclusion of the first presentation on laser physics. I think that'll be very helpful, and the next thing to do is watch the tissue interaction video where we talk about the different affinities that different wavelengths have toward different tissue types.